Welcome to Lecture 21. We're now in our second lecture on scattering. If you recall from last time, we derived the Lippmann-Schwinger equation, which said our full scattering wave function psi was equal to psi 0 plus 1 over e minus h0 plus I delta v hat psi. We're going to examine this in coordinate space by multiplying by an x bra on the left and introducing a completeness sum, which is really an integral over x prime with a ket bra sandwich or ket bra product that's equal to unity between the fraction and the v. And what we'll find then is we get a psi of x is equal to psi 0 of x plus the integral dx prime of x 1 over e minus h0 plus I delta x prime v of x prime psi of x prime. We now introduce a complete set of states given by momentum states in either side, to the left or the right of the fraction, it doesn't matter. And then what we'll find is that we're going to get the plane waves. Xp is e to the I xp over h bar divided by square root of 2 pi h bar. And h0 acting on p is just equal to p squared over 2m. That's a number because the momentum eigenstates are also energy eigenstates for the free Hamiltonian. And so we get an integral. So then the matrix element x 1 over e minus h0 plus I delta x prime is equal to the integral dp e to the I xp over h bar e to the minus I x prime p over h bar divided by 2 pi h bar divided by e minus p squared over 2m plus I delta. We can then join those exponential factors together and we can move out that factor of 2 pi h bar, and then we can factorize that denominator into a square root of e plus I delta minus p over square root of 2m and a square root of e plus I delta plus p over square root of 2m. Now that integral is a one-dimensional integral. It can actually be integrated by the method of residues. And if you don't know how to do that, don't worry, but then you just have to trust that I'm going to tell you what the correct answer is for that integral. If you do know the method of residues, you might want to try to work it out with the method of residues. The key is that you're going to have to pick whether you close the integral in the upper half plane or the lower half plane, depending upon whether or not the x minus x prime is positive or is negative. Okay? So when you go through and you work that out, the answer you get is minus I over h bar square root of 2m over 2 square root of e. Theta of x minus x prime, this means we're looking at the case where x is bigger than x prime. In that case, you get e to the I square root of 2me over h bar x minus x prime. And then plus theta of x prime minus x, this is the result you get when x prime is bigger than x. You get e to the minus I square root of 2me over h bar x minus x prime. So you see you get complex conjugates depending upon whether or not x is bigger than x prime or x is less than x prime. Okay, we can simplify those factors in front. We're going to actually bring a square root of e in the numerator, and then we'll get minus I square root of 2me over h bar divided by 2e times the sum of these two exponentials with the theta functions. We're going to let k equal the square root of 2me over h bar, and we're going to choose psi 0 to be e to the I k dot x. That's an incident wave moving to the right. And then the equation we get is that psi of x is equal to e to the I kx minus ik over 2e, integral from minus infinity to x, e to the I k x minus x prime v of x prime psi of x prime dx prime, minus ik over square root of 2e, integral from x to infinity, e to the minus I k x minus x prime v of x prime psi of x prime dx. Okay, so we have to separate that integral at x prime equals x because we have this theta function in that matrix element that we were evaluating. Okay, what we can now do is we can write e to the I k dot x. We can factor that out of the integral, and then we'll have e to the I kx times 1 minus ik over 2e, integral from minus infinity to x, e to the minus I kx prime, v of x prime, psi of x prime, dx prime, and then minus ik over 2e, e to the minus I kx, integral from x to infinity, e to the I kx prime, v of x prime, psi of x prime, dx. We're going to look at the limit as x goes to infinity. In that case, the first integral is the thing that dominates, the second integral is going to go to 0. And then what we find is what we call the transmission coefficient. So this is what the wave function looks like as x goes to plus infinity. That's when we're very far away from the scattering center. That's going to be the coefficient of the e to the ikx term. And that coefficient is given by that term in the parenthesis. It's 1 minus ik over 2e, integral minus infinity to plus infinity, e to the ik x prime, v of x prime, psi of x prime, dx prime. If we look at the limit x goes to minus infinity, we can pull off the r, the reflection coefficient. And that reflection coefficient is the coefficient of the e to the minus ikx, because that's the wave that is going to be moving to the left. And so that r coefficient is minus ik over 2e, integral from minus infinity to infinity, e to the ik x prime, v of x prime, psi of x prime, dx prime. All right, so since psi is a scattering function to the right, we often like to indicate that in the ket. So we'll often write psi, ket psi is equal to ket psi horizontal arrow pointing to the right. And then we'll write the psi 0 if it's e to the ikx as ket psi 0 with the right arrow, and e to the minus ikx is ket psi 0 with the left arrow. And then what you find is we would write r right arrow is minus ik over 2e, psi 0 left arrow, v hat psi right arrow, and t right arrow is 1 minus ik over 2e, psi 0 right arrow, v psi right arrow. Okay? You may or may not like this notation. I'm just introducing it to you as a way that kind of gets you in the right mode of recognizing which direction these different waves are moving if we were to put them into wave packets and so forth and put in the time dependence. Okay, now we can also look at a formal solution via what's called the Born series. And I want to remind you now about the expression that we got when we were looking at the Wigner-Brillouin perturbation theory. For Wigner-Brillouin perturbation theory, we had an expression that looked like this, where we have a psi is equal to a psi 0 plus 1 over e minus h0 plus I delta v psi. Now what we did then was we brought the two v's to the left-hand side and got a geometric series and multiplied by the inverse, which was a geometric series, and multiplied that times the psi 0 and got a full series. But you can actually think of this as kind of a form of Wigner-Brillouin perturbation theory for scattering states. And the idea here is that if we solve it iteratively, which was something I mentioned to you in the lecture, we're going to iteratively solve for the psi by first plugging in the approximation that psi is equal to psi 0 and then developing a series for it. Okay, so if we combine these two terms on the right and multiply by the inverse, we get psi is equal to 1 minus g0 plus of ev, whole thing inverse acting on psi 0. That g0 plus is just 1 over e minus h0 plus I delta. Then the reflection coefficient is minus ik over 2e, psi 0 ket v 1 minus g0 plus of e v inverse acting on the psi 0, and the t is 1 minus ik over 2e psi 0 v 1 minus g0 plus of e v inverse acting on the psi 0. The v we get because when we look at the expression for the r, it was a psi 0 v psi, and here we've got the expression for the psi. We have to just make sure we don't forget to put the v in. I apparently forgot to put the v in when I first wrote these notes, which is why there's that little note saying v not in the scanned notes, because I've now rescanned the notes so that the v is in there. All right, and as before, we expand that expression, the complicated expression, with a geometric series. So we do that for the psi, and we can plug that in for the r and for the t. You can see how the r and the t are kind of like the energy eigenvalue in the Wigner-Brillouin perturbation theory. So we'll get that the r is minus ik over 2e, the sum n equals 0 to infinity of this big series, and we get a similar thing for the t. If we truncate this at n equals 1, that is called the Born approximation or the first Born approximation. And it turns out in many cases, because scattering tends to be a weak thing that we're looking at, we often stop at the first Born approximation because that's all we need to get reasonably good results. So if you plug that in, what you'll find is psi Born is equal to e to the I kx plus the integral dx prime g0 plus of x minus x prime v of x prime e to the I kx prime. And you can similarly work out the expressions for r born and for t born. I'm not going to reread those for you. They're right in front of you so you can see them. Since we assume that the v is small, r born is going to be approximately 0 and t born is going to be approximately 1. And essentially what this means is the Born approximation works well when most of the wave is transmitted. That's what you get when the scattering is weak, because the wave just goes through whatever it is you're scattering. Okay? And as I'd mentioned before, with all perturbation theories, the perturbation theory really only works when the scattering is weak. But the one thing that you should keep in mind with scattering is if the incident wave that comes in with very high energy, then even if the potential is strong, I might be in the vicinity of the potential for only a very short period of time. And so the effect can be weak. So the weakness for scattering is not necessarily the same as weakness of the potential. I just need to have a weak effect on the thing that I'm scattering, and then this notion of weak scattering is an appropriate thing. Okay? Now we're going to end the lecture by talking about three-dimensional scattering. In this case, we have an incident wave, which is typically a plane wave. It will scatter off of something that is cylindrical symmetry, and then everything moves outward from that cylindrical symmetry in spherical symmetry will move out from that scattering center as spherical waves. And this is similar to dropping a stone in a pond where you see the circles move out, but it's in 3 dimensions because it's spheres that are moving out. So in order to do this, you have to recall the expansion of the plane wave and spherical harmonics. I hope that you have done this in the first semester. If you have not, please let me know. I do have some notes I can share with you on this expansion. In the past, I have gone through this expansion in class, but it is something you should have seen in the first semester. But again, if you have not, please let me know, and I will share those notes with you. E to the I k r cosine theta is the sum L equals 0 to infinity of 2L plus 1 I to the L JL of kr. JL is the spherical Bessel function. PL cosine theta, that's our associated Legendre function. And E is equal to h bar squared k squared over 2m, which means k is square root of 2m e over h bar. We've already seen that earlier in the lecture. So the JL of kr, the spherical Bessel function, can be written in terms of the ordinary Bessel functions as square root of pi over 2kr, big J of L plus a half of kr. And as we'd mentioned before, PL of cosine theta is sometimes called the Legendre polynomial, or it's called the associated Legendre function. Now, you also have to recall the asymptotic limits of the spherical Bessel functions. They go like 1 over kr sine of kr minus L pi over 2 for r going to infinity. So our radial wave function, FL of r, will go like CL sine of kr minus L pi over 2 for r goes to infinity. Remember, FL is r times the radial wave function, so that got rid of the 1 over r dependence in the JL. And I can rewrite that sign as a difference of the two exponential factors with the opposite signs in the exponents. The one that is a positive sign is the outgoing wave, and the one that has the negative sign is the incoming wave. Now, for an interacting case where V of r goes to 0 faster than the centrifugal potential, we expect that the F will go like some constant, AL of k, times the incident wave, e to the minus I kr, plus a reflective wave, RL of k, e to the I kr, as r goes to infinity. Now, the key thing here is nothing can transmit through r equals 0. There's no such thing as a spherical coordinate with a negative r. So everything is actually reflected, which means the modulus of r is going to equal 1, but it can have a phase to it. And all of three-dimensional scattering is about determining the phase. So r is given by e to the I phi, a phase, and you can prove that simply by using the fact that r plus t is equal to 1. If t is equal to 0, r is equal to 1. That's the square of little r, so little r must be e to the I phi, which is a complex phase. So we typically write RL of k in this completely abstruse and complicated way, minus e to the I 2 delta L of k minus L pi delta L of k is then called the nth partial wave phase shift. So if we plug that into the expression, what we find is we can rewrite that scattering wave, the e to the minus ikr minus r e to the ikr. We can rewrite that as al of k e to the I delta L of k minus L pi over 2 times 2I sine kr plus delta L of k minus L pi over 2. And we typically write that then as BL of k times the sine of kr plus delta L of k minus L pi over 2. Okay, and one of the reasons why I really don't like scattering is we end up having to work with these long, complicated expressions that involve the partial wave phase shifts and these spherical Bessel functions or their asymptotic limits in terms of sines or cosines. Okay, so let's see how that works. We're going to look at a free case where v is equal to 0 and delta L of k is equal to 0 for all L and k. That's essentially a trivial case. We're going to now look at a less trivial case, which is a spherical well. The well has a width a. That means my scattering center is kind of like a leaky ball with a potential minus v0 and a radius a to the ball. We have two k's that we can define. K1 is 1 over h bar squared of 2m e plus v0, and K2 is 1 over h bar squared of 2m e. The free particle waves will go like K1 for r less than a, and they'll go like K2 for r greater than a. And now we have this matching condition. We just write our RL of r as AL of E, JL of K1R for r less than a, and then BL of E, JL of K2R, plus CL of E, eta L of K2R for r greater than a. If you remember, when we work with a spherical particle in a box, there are two possible spherical Bessel functions, the j's and the etas. The etas are singular as r goes to 0, so we get rid of them because of the singularity, which means for r less than a, I can only have the j terms. But in the region where r is bigger than a, I can have either a j term or an eta term. And you have to just keep that in mind when we work on these kinds of scattering problems. Again, this is another reason why I'm not a huge fan of working on these kinds of scattering problems. All right, and then what we have to do is we have to match. We have to make the psi continuous and the derivative of psi continuous. So we get AL of E, JL of K1R is equal to BL of E, JL of K2A. I'm sorry, I said R, I meant K1A, and plus CL of E, eta L of K2A. And then continuity of the derivative will bring in a K1 times a JL prime, a K2 times a JL prime, and a K2 times an eta L prime. And now there are identities that these spherical Bessel functions satisfy for their derivatives, or we can just solve this directly for the ratios of BL over AL and CL over AL. And that's all that we will get in the scattering expressions because there's a normalization constant that goes out in front, but the scattering coefficients come just from these ratios. So by solving this, we can then get the scattering coefficients. This is what you get for the ratio. And again, you can see these kind of messy expressions. They're just really not pleasant to work with. You should note as well that if you are going to be working with these, that the eta L of rho will approach minus 1 over rho cosine rho minus L pi over 2 in the limit where rho goes to infinity. So with that, you can actually determine lots of different properties of these things in those different limits. All right, that takes us to the end of Lecture 21. In Lecture 22, we are continuing on the scattering theme. We have 3 more lectures on scattering. All of next week will be on scattering. So that takes us then to the end of Lecture 21.